So the next speaker is Arno Kuijlaars from LEUVEN, and he will speak about matrix-valued orthogonality and random tiling.
Okay, thank you very much, Filippo. Thanks for organizing this this workshop, this semester here. It's very nice to be here. I feel very welcome, and it's here in Florence, and they even named the river after me. So I very much appreciate that. So I'd like to talk about matrix-valued orthogonality and random tilings. So there were several talks already during this workshop here on random tilings, and I want to give a sort of perspective on this via these matrix-valued orthogonality, right? Which was something that was developed together with Maurice Duits a few years back. And so, okay, it still remains to be seen how it compares to other approaches, but okay, we'll see what I mean. So I will focus on this model, which is a random tiling model of a hexagon, ABC hexagon, right? So the side lengths are integers, ABC, and you can cover it with these lozenges of three types. Okay, so here you see there are different colors, right? So you have the box in this, with this shape. It's convenient to put it in this shape because of the coordinates. And then this yellow lozenge going up. This will be the, and then there's also a red one. Yeah. And so there are many ways to cover such a hexagon with these lozenges. And so from a probabilistic model, this is a very rich probabilistic model. You can put some probability on what you, on these tiles, depending on the shape, the type of tile, and also on the location in the hexagon. And then you can sample from such a probability measure on this all set of, and see what happens. In particular, in the large scale limit, you find nice pictures. Okay? So here, so yeah, so these, so the probability is generated by putting a weight on each tile in your matrix. Sorry, in your tiling, and then this will be give rise to a weight of a tiling, just being the product of all the tiles in a certain tiling. And the probability of a certain tiling is then proportional to its weight, right? This is a general construction of like a Gibbs measure on such tilings. And I will focus on a periodic weighting that so the weight will depend on the position where you find your lozenge in a tiling, right? So that is denoted here with this coordinates x, y. X, y will be integers, right? Because I'm assuming that all the vertices of all these tiles are on the integer lattice. And so for each type of tile, there is a certain weight function that depends also on the location where this box, for example, appears in the tiling. And the periodic weighting will mean that, yeah, this is periodic in both the x and in the y direction. Okay, this is what I mean by a weighting that's periodic. And so the period P will be the period in the horizontal direction, and Q in the vertical direction. Okay, and something similar, you have it with the same periods for the other types of lozenges. Okay, and then you can do simulations. Well, yeah, this is for a model where the period is 1 and 2. So it's still the same in the horizontal direction. It doesn't really depend on the P is 1. But in the vertical direction, there's a period 2. And then you may generate such a picture if you do a sampling from this probability measure for a certain choice of your weights, right, which I didn't specify here. And then you see some limiting behavior if the sizes increase, right, or decrease, depending on your point of view. So there is this phenomenon of an Arctic region where you only find one type of lozenge here near the corners. But here there's also some frozen region with two types of lozenges actually that will survive also in the limit. And here in the middle there is some disordered region where all three types of lozenges appear, right? And there, in the limit there will be a boundary curve that separates the regions. And these are known as frozen and disordered region, or sometimes known as liquid or rough. This is the tiling that you get with uniform probability. So the period is just one for both, and then there's an Arctic circle that will separate the frozen region from this rough region. If you put higher periodicity, and here is a sample of a situation where you have 2 and 3, so it's 3 periodic in the vertical direction, maybe it's actually all the way around, and P is 2. Then there is another phase, another region coming in the large limit, and that's sort of indicated here. This piece here, and also over there, this is known as a smooth region. There's still randomness there, so it's not a frozen region where everything is sort of fixed. You only see, you see a rigid pattern here. But here correlations between tiles, they decay at an exponential rate in terms of the distance. And so these smooth, I mean, all these phases were classified by Kenny and Okonkwo of Sheffield some way back. And this is then part of this, what they call it's also sometimes called the gas region, but people now prefer to call it the smooth region. Right. There's a similar model where this was actually first studied in more detail, which is known as the Aztec diamond, but that you can cover with dominoes, tilings of a square. And then this was analyzed by Chita and Johansson, and Johansson talked about it in this workshop. And there's also work by Bergen and Duits and others, and there you find this smooth region here in the middle, right? And so but this Aztec diamond is somewhat a similar model than the hexagon, right? So, but yeah, for the things we want to do, I want to do are motivated with what one can do for the Aztec diamond. Okay, so first of all, there is a deep structure here, well, there is a important structure here, namely that these positions of these lozenges in a random tiling, they are a determinantal point process. So what does that even mean? Well, it means the following. So you can focus on a particular kind of lozenge. Right? You can focus on one or two of them. I've chosen here to focus on 2 of them, but it's all equivalent in a way. Suppose you have a random tiling and you ask yourself the question, is there a tile of this type or that type at each of a certain number of positions, right? Okay, that's an event that has a certain probability, and such a probability can be expressed as a determinant of a certain kernel. The K is called the kernel, and that's what's known as the correlation kernel, and it depends on 2 variables, but each variable is a coordinate pair, right? So if you see 4 variables in a way. The 2 kind of positions that you may have in your hexagon that you take all these positions, you put them in this n by n matrix, you evaluate the kernel at each pair of positions to make an n by n matrix, and then the determinant of that matrix gives you this probability. Right? So that's quite remarkable, and it shows that there is a lot of structure here in this model. Right? That's in a way the integrability, right? That's why I'm allowed to talk about this in this workshop. Well, there's also randomness, right? And we hope there's also universality. Okay, so everything's okay. So the task is then to get your hands on this kernel. And there are two basic approaches to this. First one is due to Kenyon, and it interprets this model and other models as a dimer model on a planar graph, a planar bipartite graph. And then there is the notion of a Castellane matrix associated with such a dimer model. And the inverse of the Castellane matrix is very much related to this correlation kernel. That's one way to approach it. And Chita Johansson and Johansson also in several works start from this point of view and try to say as much as you can about this inverse Castellane matrix. In particular, getting asymptotics in an appropriate limit. Right? Another model is by considering this tiling problem of a hexagon in terms of non-intersecting lattice paths, and there is a way to count such lattice paths that are non-intersecting by means of a combinatorial lemma called the Lindström-Gessel-Viennot lemma, and that allows you to express the probability, the joint probability density function for having particles at these kind of positions here at all kinds of places in terms as a product of determinants. And then it was shown by, in an even more general context, by Arno and Mehta, this gives rise to a determinantal point process, and they have a way to get the kernel. Okay, so what are these exactly, these non-intersecting paths? Well, the non-intersecting paths is like the height function that you may associate with a tiling, right? You can also view a tiling as in a three-dimensional point of setting, right? And with boxes that you put in a corner. And these are basically the height functions then that you have. And you see, there's a choice that I make here, letting the paths go from left to right, right? And then you see that such a box, this type of lozenge, will have a horizontal step on such path. And these types, the yellow types of lozenges, will have a step up if you go from left to right. And the other types of lozenges, the red ones here, the paths are not on any of those, right? And so they are sort of, the paths don't see those. So if you take this point of view, then you don't want any weight on these paths, meaning that the weights are all one, right? But this you can actually do without any loss of generality. You can have an equivalent weighting where all the weights of these tiles are one, and that generate the same probabilities. So that's what we will do. And then, so I'm going to continue in this approach, okay, with these non-intersecting lattice paths. Then this can be encoded by a transition matrix that you have at the horizontal coordinate x. Call it T. And so this type of lozenge means that your path is going horizontal. It keeps it the same height. So in this transition matrix, it depends on two coordinates, two vertical coordinates, y and y prime, and you stay at the same level. So y is y prime if you have this box here, and then you put on in your matrix the weight of the horizontal tile of the box tile here, and you go up from y to y plus 1 if you have this other type of tile there, and that's why you put this on the first diagonal, super diagonal, and the other entries are just 0. And I want to consider this as a matrix over the integers in both, so it means infinite in both directions. Of course, only a finite part of it will actually play a role in the probabilities. And in case of periodic weighting, these transition matrices are block tuplets. So if you follow what happens along, there are two non-zero diagonals, and because of the periodicity, actually we only need the periodicity in the y direction, in the vertical direction, or the periodicity is period length q. Things start to repeat after q steps, so that means that it's a block tuplets matrix here, infinite in both directions, with blocks of size q times q. And associated with a block tuplets is a block symbol that just takes these blocks, which are size q by q. The diagonal block, you just take it as a matrix. The first upper block, you take as a matrix, but you multiply with z. And then, in a general context, you would continue with z squared and so on. But because all other blocks in our setting here are 0, this is all. And if you have blocks on the other side, they go with negative exponents of z, but they're all not there. This is like a generating function for these block tuplets matrix, called a symbol. So this symbol will play a role in our formula. So with Maurice Duits, we have a formula for the correlation kernel in a periodic setting. The main importance is the periodicity in the vertical direction, but I'm stating it for the particular case when there's also periodicity in the horizontal direction. And so it is essentially a reformulation of the Einar Meta result, but the Einar Meta they have a formula in terms of a double sum formulation, and we have instead double integrals, right? Which are sometimes more convenient if you want to take limits. But let's have a look at it. So what I state here is for the kernel on the diagonal, and I also, for convenience, I am also taking points that respect the periodicity, right? So the first coordinate is a multiple of p. The second coordinate here is a multiple of q, just to get the nicer formula. Well, nice. I mean, it's still maybe not too attractive here. So what do we have here? We have a double integral over a contour going around 0. That's gamma, of some matrix valued object. So the integral are just done entry-wise. So whatever is here will be a q by q matrix. And this correlation kernel at these particular values will be the 0, 0 entry. So the labels for the matrix go from 0 to q minus 1. Okay, so there is this A. What is A? A is the product of all these these block symbols that you get for each x, and the product goes over one period because it has a period p here. You have A0, A1, and then AP1. Then things start to repeat. I take the product over one period, and this appears here and here with some integer exponent here, or non-negative integer exponent. Okay, the L and also the M and N refer to the size of our hexagon. I also took for convenience the dimension of the hexagon that fit nicely with the periodicity, namely that A and C are multiples of Q, of the vertical periodicity, and the sum B plus C is a multiple of the horizontal periodicity, just also again for convenience. And then in the middle here, there's another object that depends on two variables. It's a polynomial in two variables, and it's a reproducing kernel for a matrix valued weight. And this gives us the connection to the matrix orthogonality. So let me first talk about this weight. What is this weight? It's some weight matrix. This A matrix to the power L, right? This is the horizontal size of your hexagon in a way. Divide by a appropriate power of Z. Okay, so what does it mean, this reproducing kernel with this matrix weight? Sorry? Sorry, I don't understand. I can't hear you. Periodic weights, and that's all. Yeah. They are encoded in this tuplets matrix, and then that appears in this symbol, this A, and so this, and in this product there are all the weights here. Well, there should be positive weights, right? But otherwise, it's and a periodic, and but that's all. That's it. Yes, indeed. Yeah. This A and that A, it's the same A. Oh yeah, so yeah, this A, yeah, sure. Sorry about that. That's a dimension, one of the sizes of the hexagon, right? That's something totally different. Yes. Yeah, yeah. Thank you for the remark. Yeah. Okay, I mean, this is one entry of this correlation kernel. If you're wondering about what is the thing in general, here it is. But I don't want to elaborate on this. Okay, if you don't mind. There's also a single integral here, and this is a okay. But again, this reproducing kernel appears here as well, again. Okay, so what is this reproducing kernel? So that's sort of the heart of the matter in a way, right? It is related to this matrix valued orthogonality. What do I mean by that? So we have this some matrix valued function that I again call a weight, but it's not related to the previous weights. Although, yeah, well, it's built out of the A's, which has the weights of that are associated with the lozenges. But I just view it as a function on the contour, gamma, and I want polynomials that are also matrix valued that have this kind of orthogonality property. So I take my Pn, which is a matrix valued polynomial of degree n, so meaning it's a polynomial in one variable, but its sizes are q by q. And I take it to be monic here. IQ is a identity matrix of size q. This times the W is again a matrix, and multiply with some c to the k, and k is some lower degree. I mean, k goes from 0 up to n here. And this integral is again taken entry-wise, and it should be 0 whenever k is less than n. So up to n minus 1, you have some orthogonality here. It's interpreted as an orthogonality. And at k is n, you have some matrix that I call Hn here. It should be some invertible matrix. Exactly, yeah, good point. This is not really coming from a scalar a positive definite scalar product, indeed. It's in a sense it's a formal thing. There's no complex conjugation here with these weights, right? It's not symmetric, there's no such symmetries. So it's an algebraic thing. So these polynomials may not exist. So with the weight coming from this model, the polynomial of degree capital N will exist. That's what you're asking? Yes? No, no. Yeah, and one feature that you have, which I would like to point out, is that this gamma is sort of pretty arbitrarily. You can go around 0 once, but everything here is analytic except for a pole at the origin. That comes from this high power of z in the denominator here. Right? So it's basically you pick up a residue of this quantity at the origin, and all this, and a whole bunch of residues should be 0. That's what this condition says. And it cannot be, it will never be associated with a genuine inner product. Which is good, which is bad maybe, but maybe it's also good, right? It depends on your point of view. Here we have the freedom to move the contour. Okay, so these are these matrix-valued orthogonal polynomials in my setting that I want. So what is now the reproducing kernel? Well, it has this property. It's a function of two variables. It's polynomial in both variables of degree at most n-1, capital N-1 here. And it should reproduce polynomials with the weight here. Here, this is again our weight. So if I multiply a polynomial of degree n-1 or less, times the weight, and then times the reproducing kernel, and integrate over the gamma and with a 2 pi I, I recover my polynomial. That's the reproducing kernel. And if, in case all these matrix-valued orthogonal polynomials exist up to degree n-1, well, you only need n-1 actually, then you can write down this reproducing kernel in terms of these matrix-valued polynomials here. In this way, as a series. But, as we already discussed, this may not be the case that all these degrees, all matrix-valued orthogonal polynomials exist. And there's another formula. For low degree, they may not exist. And also for very high degree, bigger than capital N, they will not exist, actually. Yes? So which one is not unique? I think it's unique. It should be unique, yes. But I want this condition on the, yeah. I don't understand the question actually. You cannot add, the Rn is limited in its degree, right? So that you, it's a, Rn, yeah, yeah. Okay. Okay, so there's another formula, and this goes in terms of a Riemann Hilbert problem that's associated with these matrix-valued orthogonal polynomials. So that's a problem you can characterize this polynomial of degree capital N, and also this reproducing kernel, express it in terms of a Riemann Hilbert problem, which is a jump problem here in the complex plane for a matrix-valued function of size 2q times 2q. And it's defined and analytic away from the contour. And if you approach the contour from the inside, there's a certain limit called y plus. From the outside, it's called y minus. And these two will not be the same, but they're connected with this jump matrix here. That contains the weight, the orthogonality weight. This is for z on the contour. And there's a certain condition at infinity that it should basically behave like z to the n here times identity matrix and z to the minus n here, q times along the diagonal, times identity plus something small. Okay, this was first expressed in 2 papers about 10 years ago, but it's a rather straightforward generalization of the Fokas-Itzkitaev characterization for orthogonal polynomials in terms of a Riemann Hilbert problem, where it's only 2 by 2. So the main difference is that the size is bigger than 2 by 2. It's 2q times 2q. But the unique solution here has the Q by Q upper block is this matrix valued polynomial, and there are some Cauchy transforms in the second column, and here there's a matrix polynomial of degree n-1. I didn't want to specify it exactly. But the reproducing kernel is given in terms of this solution of the Riemann Hilbert problem as well, and again also with its inverse in this way. So again, it's a Q by Q valued thing, and you take Y and take the first block, the first Q columns here, and take the last Q rows of the inverse, multiply, and that's what you do, and then this prefactor, then you get the reproducing kernel. So that's the formula. So everything is encoded in this Riemann Hilbert problem. Okay, so there you have it again. So that then gives a principle, a challenge, a roadmap how to possibly get asymptotics. What do you want to do? Well, first of all, you want all these sizes to go to infinity, probably, and at some rate proportional to each other. There, and you want to get then asymptotics for this Riemann Hilbert problem, the Y here. That will give, then you get information about how these polynomials behave when the degree grows, right? But also this reproducing kernel. And then once you have good information about this, then you may try to use that to get information about the large n behavior of this double integral, which then in turn will give the correlation kernel. And if that works, I mean, at the end of the day, we would like to identify these frozen, rough, and smooth regimes and the boundary curves in as great detail as we possibly can. This was done successfully in the paper with Maurice Duits for the Aztec diamond with 2 periodic weights. For the hexagon model, we're not there yet, so I cannot do this plan to the very end. And actually, what the asymptotics of the Riemann Hilbert problem is also to be done. But I will tell you some idea that we have, and how much time do I have? Okay, till 10 minutes or so. What kind of ingredients will be important for this asymptotic analysis? The asymptotic analysis of these Riemann Hilbert problems is usually done with a method of steepest descent that's named after Dijft and Zhou, who first came up with this method almost 30 years ago. These are explicit transformations of the model of the Riemann Hilbert problem in order to reduce it to simple jumps that are close to identity matrix. And so, but for these it's a method. I mean, it's more like a guideline. This is what you can do in cases, right? It's not something that works automatically. You have to work yourself. Okay, so what is the thing that's going on? I mean, the thing is that going on is that this matrix orthogonality can also be interpreted as scalar orthogonality on a Riemann surface. So that's a new insight, actually, for these kind of weights, okay? So how does that work? What's the Riemann surface? Well, it's associated with just the characteristic equation for the matrix valued part here, this A, right? So that's an equation between lambda and z, right? A polynomial equation in 2 variables. There's a Riemann surface associated to it. I mean, assuming that the algebraic curve here is irreducible. But then what happens is that each row then of this matrix valued orthogonal polynomial, you can build out of that some meromorphic function on this Riemann surface. which has orthogonality properties with respect to a scalar weight. That's built out of the weight here. Lambda denotes the eigenvalue here, that's as a function on the Riemann surface here, to the power L, and Z is also another function, of course, meromorphic function on the Riemann surface in the denominator. This is sort of an imprecise formulation. Let me show you use an example to show you what I mean. So the example is with period 3 in the horizontal direction, Q is 2 in the vertical direction. We get 2 by 2 matrices, but we get three symbols here, A0, A1, A2, and then they alternate, okay? Well, A0 and A1 are the same, and they are just corresponding to the uniform model. All coefficients are 1 here. And in A2, I put in a parameter A here, some positive parameter here that sort of breaks it away from the uniform model. If A is 1, we get the uniform model again. But this is sort of one parameter deformation of that. Okay, then I took the product, right, just to show you that I can take products of matrices. This is what it is. Doesn't really matter. You can calculate the eigenvalues, and they depend on Z, but there's some branching here at 3 points, at 0, at some negative number x1 and negative number x2. And so it means that these eigenvalues are meromorphic functions on this elliptic Riemann surface, right, with 2 sheets associated with this cubic equation here. And the genus is 1, except if A is 1, because then you may verify that x1 and x2 coincide if A is 1, and then we come back to genus 0. Okay, then if you want to make transformations of the Riemann Hilbert problem, and this is actually what worked for the Aztec diamond, the first transformation makes use now of the eigenvalue decomposition, spectral decomposition of our matrix A. So we write it in terms of the eigenvalues in this diagonal matrix lambda and eigenvectors that are in the columns of this matrix E. And then this transformation can be done. Right? We can use this transformation. E is size 2 by 2 here, and the whole thing is size 4 by 4. If you then look at what happens with the jumps in the Riemann Hilbert problem, on this gamma, we had identity jumps here along the diagonal, but the 2 by 2 right upper block becomes a diagonal matrix, right? The lambda is here to the power L and divided by this scalar function. So that's a useful thing, that this becomes diagonalized. There's something actually happening that these eigenvectors will also have branching along the same cuts, right? This is sort of the cuts that you have between the sheets on the Riemann surface, and the 2 columns, the 2 eigenvectors are elliptic continuation if you go from one to the other, and that's encoded by this jump matrix that has this simple permutation matrix here, sigma 1, up here and down there. Okay, now this now can be seen as how can this now be seen as a meromorphic function on the Riemann surface? If you take a row of X and look at the jth row, take the first 2 entries of the jth row, right? xj1, xj2. This jump matrix here tells you that they're analytic across the contour gamma. This identity block here. And if you view xj1 on the first sheet of the Riemann surface and xj2 on the second sheet, then this jump here with this permutation matrix sigma 1 tells you that they're analytically continuations of each other. So they are a meromorphic function on the Riemann surface with a certain pole at infinity, right? And no other poles. The order is about 2n. It depends on J here, and may also depend on this precise choice you make for your eigenvectors, approximately. Now, if you look at the third and the fourth entry of the same row, you again have this identity block here in the jump on gamma. Oh, no, yeah, you look, now I want to look at, I want to look at this block. No, I want to look at, no, they will have a jump on this gamma. But here, this sigma 1 here acts on the third and the fourth column. This still indicates that if you put this on your third sheet and that on the fourth sheet, sorry, this you put on the first sheet and this on the second sheet of your Riemann surface, they connect from sheet to sheet. But there will be, and they will have a 0 at infinity of a certain order, approximately 2n again, because of the asymptotic condition, which is now with a minus sign here. If you look at the jump on the contour gamma, you'll get that this was the function phi with a jump on the contour gamma. The jump is related to the fj, the meromorphic function, times this function on the Riemann surface, coming from this upper block here. And this then will lead to orthogonality with respect, if you multiply this now with some holomorphic differential, it will be 0 for a lot of holomorphic differentials, sorry, meromorphic differentials, with a pole at infinity only, right? And so this is what I mean. And so we are dealing here with a meromorphic function with a lot of poles, all poles at infinity, which has a lot of orthogonality with respect to, say, holomorphic differentials, again, of meromorphic with all, again, only poles at infinity. There are little details that vary from case to case, but this is the basic thing. And then this question that will be important for the asymptotic analysis is to know what happens now to the zeros of this orthogonal meromorphic function. And these are some plots for this projected onto the plane here. This is on one sheet and this is zeros on the other sheet. And there's this various parameters A that you may take. And so there's a transition here from a curve that's, you should think about it as being on first sheet and then going on to the second sheet along the cut. This piece starts to separate itself from the rest and then goes here. But what we see is that these zeros tend to accumulate along certain contours. That happens for these meromorphic functions, but what the plots actually show are the zeros of the determinant of the matrix valued polynomial, but they behave in the same way. This parameter A that I had in this model here. Yeah. Now, this is still work in progress, and I have to conclude. An observation is that if you would do it with period 2 at most in both directions, then the Riemann surface has genus 0. You can map it to the Riemann sphere, complex plane, and it becomes scalar orthogonality. Okay, and this is what I worked out in my paper with my student Ellen Groot from last year. In that case, we can find, we can use notions that exist from logarithmic potential theory to characterize the limits of these scalar orthogonal polynomials in terms of equilibrium measures and external field. But an additional problem here is to find the good contour, because you can take any contour going around 0. We need to find the right contour, and this is already known from other works, from other people. We need the so-called S-curve with a certain symmetry. I will not go into that. And this S-curve is also then known to be a trajectory of a quadratic differential. This was worked out, again, some 10 years ago by Martinez, Finkelstein, and Rachmanov in quite some generality. But the ideas go back to the 80s. In the higher genus case, we need to adapt our setting to the case of a higher genus Riemann surface. Instead of the logarithmic kernel, we need the bipolar green kernel that's associated to this Riemann surface. And we need to develop analogs of equilibrium measures, S-curves, quadratic differentials, and other stuff. And we're working on that also with Marco Bertola. And we hope to have a first paper, because we cannot do everything yet, coming soon, hopefully. Okay, so there's still lots to be done. It's not the end of the story, and I mean, far from actually. Hopefully, this will be a main tool to be able to analyze the Riemann Hilbert problem in the asymptotic, do the steepest descent there for at least some relevant cases. And if that is successful, then we still have to do a steepest descent of integrals, right? Okay, we'll see about how if we're successful ever with doing all that. But this is what I wanted to talk to you about today, and thank you for your attention. Sorry? Yeah, there will be several criticalities that can happen. You this transition is looking back at this picture. There's a transition also already in genus. This is genus 0 case. There's also already a transition into genus 0 case when these two. This is now one connected disordered region, but it could separate. And that's one transition that you would also see in the behavior of the zeros. Yeah, but there may be other transitions that. This will be a tech node here transition. Even more complicated than that. But it's related to Palevate too. It's more involved than PRC. Yeah, two PRCs coming together, if you wish. Yeah.
I also have a question about that picture. So there is those new region there with vertical.
Yes, yes.
In the asymptotic shape, are they flat or?
Yeah, this is flat. Yeah. Yes.
Then you go to the next. Yes. So in this picture, they are so in the very center of this picture. Yes, the correlations is A exponentially.
Exponentially with respect to distance. Yes.
Okay.
Yes.
Other questions?
So this case have the p equals 2, q equals to 3. How far is that from finishing your program in that case? I mean, is that?
Yeah, so that would be something that we like to solve, right? So maybe we did like maybe 20% of the things we have to do, I think. But yeah, but my feeling is that this is an essential step in that direction. Well, we can, based just on the experience with this model, right? We can sort of have a feeling for what should be going on, right? That the position of this Riemann surface and also this matrix valued polynomial is a global object, right? So it refers to the whole picture. If you focus at a certain position, then you have to do with the steepest descent analysis of integrals. You will be doing analysis on the Riemann surface, and there will be saddle points that float around on your Riemann surface depending on where you want to look here. And so, and here in this smooth region, all saddle points should be in this gap that you have because it's a genus 1 case. The region, the interval between the two cuts. Presumably, right? That's what I would expect. And when saddle points collide, right, then you would find the boundaries of these. But to have really a description of this, right? Even a justification of this, that we still don't know. Yeah.
Maybe a related question. You have started your analysis essentially from first principle. Say that somebody comes and tells you some ingredients on the solution. Say, I have a partial heuristic description of the, for example, of the Arctic curve or some other properties of the model.
Yeah.
There is a way of injecting that at a later stage of your Riemann Hilbert problem in a way of, say, like if you have to solve differential equations, and if you don't know anything, well, that's hard. But if you know something, maybe you can find it easy.
Yeah, good question. I mean, the analysis of the Riemann Hilbert problem, you need indeed as an input certain things that if you're successful, you are able to prove. You don't have to prove everything from the beginning to know. But the shape, the limit shape of these curves, or the limiting, that I don't think will be useful as extra input. So we will use as extra input these equilibrium measures, for example. And then, if we're successful, we can prove that the zeros of these meromorphic functions indeed follow certain curves with a limiting density given by this equilibrium measure. So such kind of things you need as input but the limiting shape, I don't think it is useful. It's useful, not for me, information for the analysis, unfortunately. Yeah, endpoints of equilibrium measure, that will be useful input, because then you can already have a good grip on the situation, actually, yeah.
Actually, I had two questions, but Pavel Bleher already asked the first one. So the second question is, how amenable is this to increasing P and Q? Like P equals 2, Q equals 3 seems to be already quite difficult. Is there any hope for 8 and 15, or?
Yeah, I don't know.
I don't know,
mean,
even 4 and 5?
If that's what we try to find out as well, right? If in the end of the day we find that P is 2, Q is 3, we have an overview of everything that goes in there, right? Maybe we can sort of say what is happening for even larger periods. But yeah, that's a wild guess, actually, how far we can